Thanks everybody for joining today and everyone listening after the fact. As said, my name is David Brown. I've basically been a sales engineer for different database companies for the last 25 years. And most, if not all of those, have been pretty much focused on real-time analysis. Yes, we did have real-time analysis back 25 years ago. It was just done very differently. So my role here at StarTree is a solution architect or sales engineer. So, when we have customers that are evaluating the product, I'm the guy that kind of answers the questions, saves them from having to read all the documents and understand them, because I do that all day. So I know where all the references are and how things work. And I'm part of a larger team here at StarTree. Once you become our customers, you also then get solution architects who help you with productionization and customer success managers and all those kinds of teams. So I'm just one part of the cog here of the technical sales side here at StarTree. Anyhow, today our topic will be high availability and disaster recovery, something that comes up, particularly on enterprise operations and big systems. I do like to be interrupted for questions, or if people disagree with what I say, that's even better. So please just feel free to jump in and interrupt me. I don't mind that at all. And with that, we'll kind of get started. Okay, so what are we going to talk about? The published agenda talks about some terms. We're going to review some terms to make sure we're all using the same language before we proceed. We're going to talk about how things have changed in terms of HADR, particularly from the days of on-premises, which I know we still have on-premises systems, so those still apply. But in the cloud, what is it about the cloud that has changed the way we think about HADR, and how is that impacted? We're going to look at the always available architecture. So if my system can't be down, what does that look like? What are the impacts of that? What are the requirements of that at a high level? And then we'll back off to say, well, what if I don't need to be up 24/7? What if I can afford a little bit of time down? What are my different options? And how do those play out in the cloud? Because again, that's kind of the recurring theme. How is this different in the cloud? And at the end, we will look at Apache Pinot in particular. How do you get HADR with that? And that will be a wrap. All right. And so with that, we'll proceed to reviewing the terms as promised. Okay, so hopefully many of you have heard these before. You may not exactly remember what the acronyms stand for, but when you're talking about HA and DR, some important terms start with something called RPO, which is the recovery point objective. And the recovery point objective talks about how much data can I lose, and in more particular, what period of time in terms of updates that I might miss if my system goes down. So example, I might say I might lose the last 5 minutes worth of data. I might lose the last 10 minutes worth of data. I might lose the last hour or day's worth of data. That's kind of a recovery point objective, knowing what you're going to leave behind in case of a disaster. The recovery time objective is going to be our primary concern. That is, how long does it take me to restore service? And it gets a little more complicated because you can talk about partial restoration versus full restoration, and how do you measure that and what's important. That can be complex. Doesn't really help us here to differentiate that. So we'll just talk about the system being either up or being down. Another common term is MTBF, or mean time between failures. That talks about, on average, how often can we expect failures to happen. Again, it has the same problem. What does failure mean? But also it's kind of talking about things in retrospect, like what has been our experience, what has been the mean time, as opposed to the first two, which are objectives or goals. This one is an actual measurement of time. It's a term that tends to not really apply well to an overall system. So in the days of hardware, where we're talking about hardware, you've got a known commodity product and certain chips in it and certain design specs. You can have experience running those things in various different data centers and collect information about MTBF. And you can kind of know for a given piece of hardware what MTBF means. For a whole system, again, we run into the problem of what does failure mean? Partially down, slow response versus inaccurate results. There's all kinds of different options. It's a very difficult number to use in this context. Similarly, we have mean time to recovery. And mean time recovery, like MTBF, is historical. It's talking about what has been our experience over a various number of failures, and hopefully we don't have a whole lot of failures to take the mean of. But in the hardware world, where if you're inside a data center, you expect machines to die. You've got enough machines; some are going to die every day, right? So you can think about the mean time to recover to replace those machines. But again, on a whole system, it doesn't help us in terms of planning because it's just always looking kind of back. And for the same reasons, MTBF is historical. It's always kind of looking back. So we're not really going to use those two terms or values in our plan, but they could be used to kind of support. Like if we have a plan and we expect that this is going to be our recovery time, we can back that up with, well, here's how long it takes to recover the individual components on average. Add those up and come up with our actual recovery time objective. Okay, so we're going to focus primarily on RPO and RTO and not really mention MTBF and MTBR and GTR after this point. Okay. So how has the cloud changed things? Well, as I mentioned in the previous slide, you kind of have to define. Oh, was that a question, Aaron? Oh, it's just AI. Okay. So what does failure mean, right? It's changed a lot because so many things, particularly either in the cloud itself or in distributed databases that have been designed to run in clouds or in large data centers or distributed over multiple machines, already have the concept of recoverability inside their own architectures. Pinot, for example, uses Zookeeper, which has always 3, so it always fails. You can have multiple servers. You can have different replica groups so that you can take one system down and replace it, upgrade it while the other one's still running and have 0 downtime. So when we talk about failures here now in the cloud, we're not really talking about failures of individual machines. We have to talk about failures of our service at a high level. When is our service either unavailable or degraded to the point that it's going to cause impact to our end users, right? But we have fewer things to think about in terms of what can fail, because at a low level, down to the RAF protocols inside of these databases or the way that availability zones work and the databases can take advantage of the availability zones, we don't really think about the system failing as often. We also have Kubernetes in many cases in the background that can detect systems are dying or failing or getting worse or degrading and replace them with other ones, with fresh ones that may not have the memory pressure or things like that. So with Kubernetes is sort of anticipating potential failures. A good operator will look at things and say, hey, this thing's still working, but I better refresh this node or put in another node or maybe even scale up to handle the load before something fails. So it's a lot more proactive. And as we're going to talk about kind of in a minute, there are redundant file systems and different products that you can use out there to distribute file systems across regions. So we tend not to think anymore about file systems failing either in the days of S3 and GCS and Google Blob or Azure Blob Store. We stop thinking about, hey, the redundancy or the fault of our system. We expect that we put the file in there, we're always going to get it back. And yeah, we can start talking about nines and how S3 is designed for 4 nines and actually achieves 6, and most people think it has 9. It doesn't really matter. It's pretty much reliable, and there aren't a lot of stories out there of people losing or having corrupted data in these systems today. So back when I started in the industry, which is a while ago, the architectures were client server, and you're basically connecting to some database. That database handled transaction information, and you wanted to be able to recover all the changes you had made up to a certain point. And initially, it was very difficult. You could run backups, and backups tended to be an asynchronous process that would go and pull a bunch of data into another file. And so it took quite a while to run. It put a fair bit of load in the system, so it wasn't something you wanted to do during peak hours. And so your recovery point objective became the time between when you ran those incremental backups, right? Those were the dark ages. Pretty quickly after that, they realized how difficult that was to manage, and they started to use things called journal file systems. So the database itself, as well as writing out to its kind of source files that it would use to query, would basically keep a journal log of the events that it had received or processed, so that you could replay that log from the last recoverable segment or block of data that you had in your database and catch up and generally not lose any information. Right? It does cause a problem where when you bring the system back online, it is basically blocked and can't be used by anybody until it has reprocessed that journaling file system to catch up, which could take time, could be in a matter of hours, depending on how long that thing is run or since a backup has been recovered. But at least you're not going to lose any information. Similarly, there's other things in our architectures now, particularly queues. Things like Kafka or MSK or Panda or Kinesis, right? And these queues typically will have a backlog of information in them. And they kind of play the same role as the journaling file system in the databases, where if I'm processing from this queue, putting it into my own versions of my files, and my system goes down or the system underneath it goes down, and I have to recover, I can probably go back in that queue to a certain point. And usually most people have a day or multiple days worth of information kind of still sitting in their queue. So we kind of have that buffer. So you combine those things all together. I hope everyone understands the terms I'm using here at the bottom of the slides: a system of record versus a source system of truth. System of record is going to have, its journaling file system is going to have to kind of depend on its own devices to make sure that its recovery point objective is low. Whereas a system of truth is always kind of relying on the system of records behind it, whether that be the database itself or the output of the CDC of that database that gets put into a queue, now being the events in the queue. Systems of truth can generally go back and rely on the system of record. Since Pinot is a system of truth, generally not a system of record, although it can be, but generally, we're going to kind of assume that we have this ability from downstream systems to go back and get every event that we should have processed. Okay, so net, we don't really worry about RPO anymore. It's not something that you have to generally worry about. It's kind of already baked into the systems that it's going to be zero or very close to zero in terms of not losing any updates or any records. Now, being able to use that feature of being able to replay, relies on event processing being idempotent. And idempotent is a fancy word that means I can replay the event multiple times with no net change. Doesn't matter how many times I process each incoming data, it's not going to change things. When you think about idempotence in an architecture, it's kind of like you always have a background thread or a daemon in your head that is every time you consider a product or feature or an API that you're providing, you almost want to always be thinking in the background, is this thing idempotent? If it is, great. If it isn't, could it be? Are there changes you can make to your architecture so that it is idempotent? Then do that. If not, okay, right? It's not an absolute requirement. We can get by with things in our systems that aren't idempotent. But you're going to want to document that well so that people are aware of that, because it could have impacts on the architecture as it grows. And you probably need to have some sort of script or process that can go through and reprocess a bunch of data to make sure that your answer, your report, or your materialized view is going to be corrected in the case of replaying data or recovering from a disaster. So if you can't prevent the damage from happening, at least you should have ways to detect it and correct it, which we'll see is a kind of a recurring theme. Any questions about that? Everybody agree or disagree? Anybody got situations where they built systems that weren't idempotent and lived to regret it? Okay. So what can cause outages in the cloud? Well, many things, but the top leaders here are human error. Someone makes a mistake, types the wrong thing, typo into a script. The scripts are usually written to protect from most accidental, things, but not always, right? Things happen. Another common one is security policy misconfiguration. So it doesn't actually take a system out, but it blocks people from using it, or blocks an administrator from being able to do something, or blocks people from being able to read. And it is common for this to happen because we're always putting in these policies. They're complex. It's hard to understand what the impacts of them are kind of downstream. And so you can make this system and block out your system. The nice thing is these ones are usually pretty easy to fix. Once you can diagnose what the problem is, you probably know, oh, that's one of the last changes I made with a secure problem. You can undo that for a minute, see how it works. But that is a common reason for outages. Resources, power, cooling, those kinds of things do fail. If you look historically, which I did, at the types of failures in cloud regions, this does come up. Big storms, big electrical storms too can cause havoc, particularly with individual data centers or even disease. Akin to that would be a local disaster like a hurricane. Don't know that we have too many experiences here in the US with this happening, but I believe in Southeast Asia there have been AWS regions that were lost or out due to typhoons. They call hurricanes over there. And as well, the clouds are pretty much well defended against cyber threats and attacks, denial of service attacks, things like that. But they're always getting better. It's kind of constantly happening, and they can cause some issues. Not as big yet as we might have thought because they're protected pretty well, but still something that can happen. Okay, so we have to be concerned about these and how often they're going to have, and then think about what kind of impact to the availability of our system do these different kinds of outages cause. And we're not going to go into the details of each. We'll talk about it at a high level.
What about upgrade failures, upgrade maintenance kind of issues or failures like during that time?
Sure. Great question. Does happen. Not the cloud's fault usually, right? That's going to be something to do with the SREs who make a mistake, right? But yes, typically when you're architecting a system and you're thinking about replication inside that system, and when you're thinking about rolling upgrades, et cetera, that should be part of how you plan how a database is laid out and used. Most times I find those things are pretty well done and well set up before you get to production. But yes, problems can slip through. Have you got an experience that fits in that category?
Sometimes, things work, but there could be a version mismatch, or when a new version doesn't handle a particular thing well. So it's not like it's fully out failure, 100% failure, but some critical transactions fail.
Yep.
So that's a kind of a partial failure, but affects has a business impact.
Yeah, it's a good point. I left it off my slides. You're right to add it in there. It kind of comes down to the age-old problem of dev test, unit test, production, right? How closely can you make those systems mimic each other, right? And the cost of doing that, right? To really prevent any kind of upgrade or any outage in your production system due to a rollout of new code or anything like that, the only answer is to have a UAT system or a test system that is as accurate as possible, close to the system. There's another reason to think too about different products that may be sharing resources. So many the products today, and Pinot isn't in this category yet. Even with StarTree Cloud, I wouldn't say we're in this category yet. But there are some products that kind of commingle all their customers' work into shared systems, right? That can be very problematic because it's very difficult to test every permutation and combination of query syntax and use case and large query and result set size, et cetera. It's hard to test all those conditions when you're building a database product and you're running through your unit tests. And so my experience in another company was that when we would deploy code, we'd find some customer whose permutations and combinations and utilizations of the feature caused a bug that we didn't simulate or didn't catch. And so, my advice there is to think about, if you're building a big system where it's really, really critical that you not use a system that is shared or deployed where everybody's code is deployed together. You want to have the option of doing it yourself when you want it on your system, running your own tests. And yes, even then you can miss things, but it's a lot better than having a version kind of forced upon you at some time without you knowing or without being able to individually specifically test your use cases. Just something to watch out for as you go into the world of SaaS products, right? Okay, good. Okay, so let's talk about the always available architecture. There's some use cases out there, like emergency services, utility grids, air traffic control, where you kind of always have to be available, right? You can't be down. And so if that's what you need, that's what you have to build. And it can be done, right? It can be done. It's just requires a lot of effort. Other systems, you might think of something like TikTok, right? Like, does TikTok have to be up all the time? Well, there's some public good, I think, of having TikTok or X or Facebook kind of constantly available. Quite often in cases of natural disasters and things like that, people are using that as a communication mechanism, so it has that effect. But those companies aren't doing it because of that. They're doing it because they want their sweet ad money and their ad impressions. And if they're down for a certain period of time, they're not charging their customers for ad impressions, and so they don't want to do that. They want to be down. They don't want to miss that opportunity. And they know that in times of natural disaster or things like that, there's a lot of activity on those sites. So it's important for them to ensure that the systems are always available. But it's going to come down into each individual use case and each individual company. Do we need this? Right. So let's assume for a minute that we do, and let's look at what's involved in building those things. So if and when we build this, our goal is to have our recovery time objective down as small as possible. As small as possible isn't zero for reasons we'll talk about in just a sec. But it's probably in the order of seconds or a couple of minutes. Was there a question there? Okay. So we're going to assume we have a system. We're going to have our system in multiple regions, physically distributed, different sides of the country, different sides of the world, whatever we want to do, right? And we'll imagine two scenarios. One, I've got someone accessing my system internally through my corporate network, or someone else accessing my system from some mobile app. One of the first things we're going to have to do if we're going to do this environment is we're going to have to ensure that the source data, if it's batch files in this case, is made available to both systems, and the underlying file systems that are storing those files have to be isolated and separate so that the loss of a region doesn't impact the other file systems availability. This allows the system to keep running and processing updates as it normally would. And we would have to do the same thing for any real-time streams, Kafka, MSK, or Panda, whatever is coming in as well. Now, in this case, if we're using something like Confluent Cloud, where the queue is hosted, we're going to rely on their high availability and disaster systems to ensure that that system is always available. If not, if we're using our own internal Kafka, MSK, some of those things, then what you're going to have to do is make sure that you've got a stream in each region, but downstream from that stream, whoever is feeding that stream is going to have to feed both streams. So you're increasing the work down there. At some point, you've got to split it into systems that are completely isolated from each other and aren't going to be dependent on each other existing. No brainer, right? Of course, you have to do this. Right? It's a lot of work, right? And you can think too about some of the costs. If I'm pulling information from Confluent Cloud and paying egress costs on my data, if I want high availability, I probably have 3 replicas in each region. So I'm pulling the event 3 times for each region. Now I'm doing that for 6 regions. I'm pulling the event 6 times. The egress costs kick up there and it starts to come into play. But that's the cost of doing business if we want to have this highly available at all time system. The hardest part of this system, in my experience, is that you have to have some sort of proxy system. Not exactly the right word, multiplexer, relay, insert your favorite word there. But it either has to be a separate service or device or API server that's providing a gateway into the different regions, or it has to be built into the logic of the client application to be able to switch. And this proxy can't run in the cloud because the cloud could be gone. So you can't go to a specific cloud and do things. You have to kind of have some logic in your app. And this can be complicated or it can be simple. But let's talk about how complicated, if you want to do it right, what that means, right? Not only does this system have to be able to detect what a failure means, it has to retry, it has to understand, well, okay, how many times do I retry on one system before I give up and go on to it? It also has to probably be able to recover in such a way. And one of the problems here is that DNS doesn't really help you, right? You can't change DNS A records very quickly. It can take a day to propagate it around the world. Granted, the clouds have some nice services like Route 53 and things like that, where you can change network resolution very quickly, but that comes at a pretty steep price too. This is a particularly hard piece of code to write and get right and test. So just understand that this is kind of one of the major requirements of going to this hot dual system view. Another problem is keeping the data between the 2 regions synchronized. And my advice here is you can spend a lot of effort trying to make sure that the feeds are exactly the same. It's not actually that hard to make that happen, but it doesn't matter how much effort you apply there downstream, you will run into situations where the data gets out of sync for different reasons. And so what I find is important here is where you want to start your effort by having scripts that can detect what is out of sync. Otherwise, you're going to have end users saying, I ran my query and I got 100 results set here on this system and I got 99 here. Why? Right? If you don't have pre-built scripts or systems to be able to go out and compare, and that doesn't necessarily mean loading all the data into something else and comparing it. There's ways you can do it, first checking primary keys, et cetera, and timestamps. You should have a script or a way to determine what's wrong or what's different between the two. And then you should have some ability to correct that, which should be inherent in your database platform or your system platform, some way to inject correcting record, et cetera. But assuming that you can do something downstream and design it so that they're never out of sync, that's not going to happen. It's folly. So let's quickly review kind of the hot scenario, pros and cons. 1, always available. That's why we wanted it. That's why we went to the effort, right? You're kind of never down other than maybe, a minute or 2 while you have to switch. You have the ability to load balance your load across multiple regions if you do this. Now, I would put it to you that if you're doing that, you don't have a hot system, you actually have a warm system. We'll talk more about that in a second, right? If I am load balancing my work between 2 systems, that probably means that one of my system alone cannot handle the full load if I were to lose the other side. And in some of the next slides, we'll talk about the problems there and what that means, but understand that if I'm load balancing, not necessarily hot. I can also take advantage of the locality of that data to support data sovereignty. So there's, different countries that have different data sovereignty rules. German data has to stay in Germany, certain data, right? That comes with a big hit too, because if I am using my regional multiple systems in multiple regions to implement data sovereignty, I now have to think of high availability or disaster recovery of that sovereign region. It means my backup or DR can't be in another region, and now I need a hot site for every one of those regions. So yes, this is an advantage, but in the end, it's a curse still. There are all kinds of nice benefits of having a hot system, because you can take a whole one down, right? For upgrades, if that's how you want to do it, right? If your proxy is under, you've got nice control of your proxy, and you can switch your clients from one side to the other very easily. It's great to be able to take a system down, update it, test with it, bring it back up, synchronize it, turn it back on. That's a great thing to have in a very large system, and a lot of work to get it to do, but very valuable. What are the cons? Well, obviously the cost. It's going to cost you more than twice to have it, because not only do you now have the resources and the software licenses and everything running in 2 regions, you now have the effort and the maintenance and the SRE work to get that thing set up and running in the first place. Right? We talked about the increase of ingestion costs. We talked about the effort of building that proxy, and we talked about synchronization. So now let's take a quick look at history and what's happened, and I'll go into more of this in a bit, but here's a data point that in 2017, it was experienced one of its worst outages, which was a 4-hour-long average. And that downtime, they say, incurred between $150 and $106 million for over 4 hours, so $40 million an hour, to the cloud's customers. When they talk particularly about the S&P 500, that's the only ones they seem to care about, right? So that sounds like a really scary number, right? $40 million an hour, right? Well, okay. If you take the US GDP in 2023 and say, okay, I'm going to spread that GDP. I'm going to say generally that GDP is generated over 60 hours a week. There's like 60 hours active hours. The rest of them we're all sleeping or whatever here in the US. So if I take the GDP of the US in 2023 and divide it by 52 weeks and 60 hours per week, that number actually comes down to $8 billion an hour. So, okay, this cloud region went out, and our customers, the impact to the economy was $40 million an hour, but the economy is $8 billion an hour. Is it that critical, right? And part of the problem of determining, what are the downtime losses, I find they're usually inflated. People will look at it and say, look, we were selling widgets at $5, each, and so many widgets per minute, we were selling all this. And then we went down, we weren't selling any widgets. And then we came back up. Therefore, this is how much money we lost selling widgets. Well, that's not true either, right? People who wanted a widget will come back after 4 hours and order a widget, right? So it'll peak after, and you catch up on a lot of that business. So I question whether these numbers determine how much is lost, and whether we should be as scared in our boots when we see big numbers like this, and run right and say, okay, now I need to double my system because I could lose, this much an hour. Well, how much are you making an hour, and how much of that will naturally get recovered, right? In fact, AWS's revenue per hour in 2022, I think, or 2023 somewhere, is in the area of $11 million per hour worldwide. So AWS itself, if you are going to say now everybody has to double their system in order to, not suffer this downline, AWS is going to make a whole lot of money because they're earning this extra compute for all this time when it's never used. But I had another point. We're going to use a whole lot of compute, all right? And we don't have that much compute. If everybody starts doubling their systems in order to have this high availability uptime, we're not going to have any compute resources left for our AI overlords to take over. So there's other costs we have to think of in terms of what it means to have hot regions. And generally those costs are so high, it actually doesn't happen, in my experience, doesn't happen as often as you think it would. Okay. Anybody want to challenge me on any of that hot stuff? We're about to move on to the other options, but is there anybody who has any questions?
The thing to look would be, is there a way you can have a hybrid where the most critical ones, if you can do hot and others, you don't have to. But determining the challenges there will be determining what is critical, and then how do you make sure that the amount of resources you spend for that is just the minimum needed.
That's all work you have to do, right? And talk to your business and find out what that information is. But the point I would make there is there are fixed costs and variable costs when you want to jump to a hot region. And setting up the redundant data feeds, the queues, those kinds of things, setting up that proxy, that's going to be a fixed cost. You're going to have to set up and manage and maintain that system, regardless of how many tables. Let's just assume that's our unit of measure. Regardless of how many tables or subsystems or APIs you want to keep up, there's the fixed cost. And then for each API or service that you want to run in that environment, well, now you've got the compute costs of those services are going to be the variable costs on top. So yes, you can absolutely do that. That's a great option. And thanks for bringing that up. That makes a lot of sense.
Well, the challenge here is, and maybe you can give us some pointers or resources to do that. Like you kind of mentioned, the cost, the fixed cost, variable cost, and then comparing it against the impact of the failure, right? If failure is going to be like you did some calculation and showed that 11 million versus some number, like it's not worth doing. The fixed costs are very high or the variable costs are very high. Right. Maybe I'll rethink that, right? Well, my question is, how does one go about doing that, or maybe some pointers or references to doing that? It'll be great.
I don't have it in my slides, but again, I think you would have to look at your system usage over time, and I bring up your system usage over time. How much revenue that's bringing in, or sometimes you can't tie it directly to revenue. You have to associate some cost of that system being down, and that's going to be different for every use case. It's hard to say. Right. And so the cost of that being down, and then the risk of how often it might be down, and then how long it would take to recover that service is kind of what we're going to talk about. But I'm sorry, maybe it'd be good a follow-on of this, we have walk through a complete example, right? It'd be nice to have an example company where we walk through it and say, well, this is why we made this decision, but I don't have that here today. Sorry.
Okay.
Yeah. Great question. Yarden, you can write that down as an ask.
I was more interested in not the business, because business varies and everybody has a different impact. But the cost in the cloud of doing that hot kind of an architecture, I thought would be more common because the databases, the streams that you use, the redundant streams, etc. So those are kind of more or less a common thing across different infrastructures. So if there is some modeling around that, the price, how much it takes, and then all it takes is for me to take that and apply it to my business and see the impact, right? So I'm looking for that other data where it's more quantifiable, right?
Sure. I'm not sure I can satisfy your question. However, the thought of doubling plus 10% the cost of a single system would be a good rule of thumb. And again, if you say there's certain subsystems that I can do without, okay, you can bring that down a little bit. But it's anything that would change that number, double plus 20%, double 10%, is only going to move it a little bit in each direction. It's generally going to be double plus a bit, right? I wouldn't expect it to be widely different than that. So, including everything, licenses, storage, compute costs, generally double.
Cooking costs as well.
Yeah.
David, we have a question from Bobby. Do you recommend any resources or books to read more on outages and high availability?
Um, I don't, but that'd be a good follow-up for me to answer afterwards and add this onto the wherever we store this thing and tack it on later. There is a nice book here at the end you can get, and I'll give you a QR code where you can get a good book that talks about kind of architecting some of the systems, and it does include a little bit of DR, but anything that was specifically for DR in the cloud, I haven't seen anything yet. There are all kinds of books out there on how to do it on premises, but they don't necessarily make the same calculations. Okay, we'll pick up a little bit because we are going through time. Just quickly, multi-availability zones. I personally don't like them. I kind of expect a lot of people to disagree with me on that point, because if you think about it, the clouds have invested massive amounts of cost and infrastructure to implement them, right? Looking back in history, about half of the AWS outages impacted only a single AZ. So that means a half were not a single AZ, a half took out kind of the whole region. And half of the half that did affect a single AZ caused degradation or some issues in those other AZs. And that can make a lot of sense, because if I've got a bunch of systems and they're working in multi-AZs and one AZ fails, well, now everybody who was using those two AZs in a multi-AZ environment is going to switch onto this other one, and so the loads are going to increase very suddenly and dynamically on those. So they help, right? And definitely, you know, here at StarTree, we can use multi-AZs if that's something that you want, and it kind of can increase that level. I question how much it does help, right? Again, it's one of those calculations you'd have to understand and do. And the cost of a second AZ you incur on every network transition. Because every network transition, if you got a distributed architecture and you're sending messages between servers, and those are going across AZs, well, now there's an extra egress cost for every piece of traffic that goes back and forth. Not only money costs from the cloud, but time costs, right? You're adding probably somewhere in the order of 10 to 20 milliseconds potentially for every transaction. It might be a little high in some cases, depends on the query, but just the extra network time, because it's not just a single ping across an AZ, you know, for every transaction, lots of stuff moving back and forth. Go ahead. Yeah. Alan, question? Oh, something in the background. Okay. Hot warm architectures.
Pick one on the previous one.
Sure.
Trying to summarize what you said, are you saying multi-availability zone architecture is a good thing or a bad thing? Because given that multi-regions is, you kind of explained, it could be very expensive, but multi-zone architecture, availability zone, is that designed to keep in mind? Is it a good thing to have? Or I'm trying to read through what he says, what he's saying here.
Sure. And I am kind of being a little coy on this one, because I know a lot of people like them. I personally don't like them. For me, I would have a system where, like, if I wanted to look at a SaaS provider, I would like my SaaS provider's platform to be multi-AZ, but I don't know that I want my database across multi-AZs because of the time and performance cost. Now, I'm highly, highly, highly biased to real-time systems. That's kind of what I've worked in, right? So please take this with a grain of salt. But if I'm not so concerned about the latency of my queries, then absolutely, this is fine. But I find the cost of this AZ, a second AZ, in terms of the performance, the extra resources, the extra costs, to be quite high for what you get, right? If what you're getting is protection in like 25%. So if we look at, you know, only half were single AZ and half of those, the other AZ didn't do so well, then in 25% of the cases, a multiple AZ helped me only. Right, so is it worth it? So that's what I'm trying to say, and I'm not giving you an answer. I'm just saying.
Okay, got it. Thanks. You got it.
Right? So warm architectures, or hot warm architecture, would be where you have a full running system on one side in one region and a warm system on another side. Similar to the hot, you still need the proxy switch, but it probably doesn't have to work as fast, so the logic can be, you know, more simple. You may be able to do it with Route 53, something like that. The problem with a hot warm system is your warm system probably has to at least be big enough to do all the data ingestion. You may not service any queries out of it, but you at least have to keep it up to date with regards of the data. So you're still bifurcating the input streams, you're still processing them on each side. It's a pretty big cost. And a lot of the systems that I build with my customers, they use more resources to ingest and process each event than they do to query it. Right? So hot warm might not be so warm. It might have to be hot hot. One of the biggest problems I have with hot warm architectures is that if you're switching, right, I've got a warm architecture in US East 1. I've got my hot is in US West 2. US West 2 goes down. How many other companies are now also trying to get additional resources in US East 1? The thing about hot warm is when it fails over, you've got to turn that warm into a hot. You've got to add extra resources. You've got to bring on more computers to meet the load, right? And everybody else is doing it at the same time. So that's probably going to stretch out your RTO, make it longer, because when you say, hey, cloud, give me a machine, it may not come back very quickly. And a lot of database or systems don't handle that failure very well. They don't retry properly because they haven't experienced. It's actually hard to experience that problem in the cloud unless you're in that situation where everybody's trying to get resources at the same time. So that's a problem with the hot warm. I think that's about it. And so the next one obviously is the concept of hot cold. What's the difference there? Well, in hot cold, you probably have nothing running in the cold side, nothing running active. So you're not really running at the same time. But with hot cold, the idea is, okay, if I lose my hot side, I can rebuild in a different region. Probably take me many hours, maybe even a day to get the system back up. But that's going to be important for a certain type of failures that we're going to talk about in a second, right? So that's a different architecture. There are obviously different hybrids. So if you think about a retail company or payment transaction company on Cyber Monday, right? On Cyber Monday, they better be in a hot environment, right? And they probably want to be load balancing across those two, right? If they're hot cold on Cyber Monday, by the time they get cold up, Monday's over, right? And if we lose Oregon on Cyber Monday, that's going to really exacerbate the warm up problem of everybody wanting resources at the same time. So if we want to make sure our system's available, we'd better ramp it up, right? In those periods where we expect a failure would be more catastrophic to our business than others. Okay. There are types of failures we haven't seen to date. I talked about typhoons in Asia, maybe taking out a region. That's kind of some of the worst, but there are all kinds of things that could happen, right? In Oregon, you have the Cascadia Fault. God forbid we have a major earthquake and the region is devastated, right? Oregon's gone, right? Or at least the region, Oregon and the rest is gone. That's when we'd want to be able to say, hey, look, everybody in the world knows that the Cascadia Fault just slipped and there's devastation here. No one's going to blame my company for not necessarily being online at that time when everybody else is offline as well. But at least in this situation where it's gone that long, I better have a plan to get back online within a couple of days. So summing up all that kind of thought about failures and the nature and how long they take, here's data from AWS in 2022. How many different outages affected the entire, well, actually, it didn't have to affect the entire region. These are just any kind of outage reported on AWS. We can see that US East 1 is dangerous, right? People say friends don't let friends run in US East 1. All kinds of speculation as to why that is. Is it different because it was the first one? It's probably more just because it's the busiest, right? As we can see Oregon's in afterwards. Net, when we look through this stuff, though, we find that a lot of the outages lasted between 20 and 40 minutes. Some of them were a couple hours, right? So if we think about what our RTO will be given our different architecture, hot, kind of 0 hours, hot, warm, takes a couple hours to get our warm system to hot, or hot cold, where it might take 6 hours to a day to start everything from scratch. Somewhere in that middle zone is going to be, how long do we expect it to take for the region we're in to recover? Right? So if it's a failure that's not a meteor, not an earthquake, but just some mistake, waiting for the cloud to recover generally takes about 20 to 40 minutes, and it's back online. And in many cases, many failure scenarios in those clouds, the error might be something in the networking layer. I've experienced a bunch where my systems running in my VPC with our own IP address and all kind of stuff were fine. They were running. They were kind of wondering, why am I not getting any queries? Because the problem was on the front end network. And those kinds of problems, once they fix that problem, your system is sitting there ready, humming, ready to go. Right? So there's not that many problems that are going to take you out for a long period of time. And we have about 7 minutes, so I should quickly talk about how this happens in Pinot. Hopefully some of you are familiar with this architecture in Pinot. Let me talk about what files have to be saved or recovered or backed up in order to make Pinot work in one of these worlds. So in Pinot, when you're ingesting from files, that's done by the systems called the minions. The minions will bring in these files, they'll process them, they'll turn them into segments. They'll write those segments to something we call the deep store. And the deep store in many cases might be S3, or it could be a SAN or NAS or something that's basically a fault-tolerant, reliable system, but it doesn't have to be fast. So Pinot's going to get its speed for accessing these files from the ephemeral storage that's associated with each of the servers. So when the minions create the segments, they're put into this deep store. The minions tell the controller, who tells Zookeeper, hey, there's this new segment, tells the broker. And now we have to think about, well, now we've got this metadata information that's in Zookeeper about where the segments are and what their names are and what information kind of generally they have, what time period they cover, et cetera. That needs to be backed up. So we've got our offline segments written to the deep store. We have Zookeeper backing up its information periodically, but frequently to that deep store. Our controller, once the segments get put in the deep store, will go tell the servers, hey guys, go load these servers. So the servers will load them up into their ephemeral storage. So they're not really accessing the data constantly in the deep store. It's just archival. And then we also have data coming in through streams. Those get pulled in directly by the servers. The servers are creating their own segments we call real-time segments. Those are also written out to the deep store. So now we've got our batch segments and our real-time segments and our Zookeeper metadata there. One more thing that we need, the server sends metadata over to Zookeeper, so that stuff gets backed up too. The last thing we would want is, if we are using Pinot's upsert feature, we would want to enable something called the upsert metadata snapshot. And what that does, when Pinot is handling upserts, it's required to have kind of an extra lookup dictionary that it keeps in memory and or RocksDB, depending whether you're using open source Pinot or StarTree, that basically say for any given primary key, I know which segment the last value is in. And that data can be recovered if we don't back it up, but it's quite slow to do that. So in order to make our recovery time objective, in order to meet it and make it smaller in our environments, we want to make sure we're upserting this snapshot. And so that's all the data that we need for Pinot to bootstrap from its world: the segments, the metadata from Zookeeper, and possibly the upsert metadata snapshots. And that means we can use something like S3's replication and say, hey, I'm going to replicate my deep store, which is in my bucket, over to some other region. And if I do have to start up a new cold system and that stuff, I've got everything I need there. And S3 replication is usually good to within a second or so. So there is potentially a little bit of an RPO there. But if you understand how Zookeeper works and how the metadata works, basically, the only thing that's really critical is the last bit of information that came in on the stream. And because the stream itself, as I talked about before, is probably caching in a whole day's worth of information, the offsets that we've processed go into that Zookeeper log. And so if we don't get the latest version of the Zookeeper log, What that means is we'll reprocess a little bit more information from the streams. Again, we're idempotent, doesn't matter, so we can do that, and everything happens back up. It just catches up really quickly, and away we go. So just to finish time, and I'll open up for questions when we're done if you want to hang out, but 3 minutes to finish. What are the things that you need to think about? What is the role of my system in the architecture? If it's a system of record, well, then I better look at something that itself is internally consistent, has a journaling file system, has a way to recover when it loses resources. What does my business need? What are our true needs from the service? What's the budget? What are my execs willing to pay for those needs? And that's an iterative process. As soon as they tell them the budget, from the budget, you can determine what is possible, which provides a feedback loop off into the needs. Like we said, okay, I can do that. Here's the cost. And then you explain to them kind of stuff that I went through, like, well, here's the risk, right? You always want to spend money to offset risk. By properly evaluating the risk, you can determine what it's worth to you. And the last and most important possible lesson at all is that a disaster recovery plan is just a plan until it's tested. One of the really nice things about hot environments where you are potentially load balancing between the two, or you're saying, hey, I'm gonna switch everything over to system B, bring system A down, bring it back up, is you're basically testing that disaster recovery mechanism and make sure that it's working and up to date every time you do that kind of stuff. So that's a really good thing. If you're not doing that, you have to be running some sort of tests on a regular basis, because you never know what update to your system could break your DR plan. So with that, I will thank you for your time. I will throw up a couple QR codes. I'll go through these quickly, and if you guys want me to back to them so that you can grab them individually, I will do so. These QR codes will allow you to join our Slack or the open source Slack, work in the community with Yarden, come to the dev at StarTree.ai, which is the center of all Pinot. You might be interested in the book that I mentioned that we talked about, Building Real-Time Analytical Systems, that will talk about these, again, in depth, kind of how these architectures work with the streams and the minions and storing things off into the deep store. And also you can come into a StarTree cloud and get yourself a trial system that is free forever, for up to a certain limit of how much data you're going to put into it, that will allow you to run the database, run Pinot in the cloud in our serverless environment forever as soon as you sign up. So with that, I will turn it back to you and any questions. And if you want me to back up to see some of those QR codes, just please ask. Anybody have any experiences that would agree with this or disagree with what I said?
Hey, this is Peter Corliss, marketing guy here at StarTree. I just wanted to point out the fact that it's not just Apache Pinot you have to watch out for. I've seen outages where it was like one microservice that never came back, right? So the cluster was up and running, but what are you connected to? Are you make sure that all parts of your architecture have high availability to them, because it's that one thing that you forgot about that's really going to hammer you. So I just wanted to—
How do you find those things?
How do you find those things? You find those things when there's a data center fire, right?
You test. You
should test.
Right?
You should test.
Right?
Exactly. Yes. And so, I just wanted to say thank you. This is a great reminder for people on how to do this kind of stuff. I love. I'm going to watch the whole thing. I only got in here a little bit late, but I just wanted to thank you guys for putting this together. I hope a lot of people got some great feedback out of this. And again, I'm looking forward to seeing the recording go live, because I think it's gonna be a hot topic.
And I apologize, guys, that if I created more questions than I answered. I'm sorry, but that's kind of the nature of this process in this day and age.
And I think we can address all of those questions at our Slack space. I mean, you can always join our Slack space, whether it's a StarTree Slack space or Pinot Slack, and David is there, Peter is there, and our team.
But I see Sankar. Sankar had something to ask there.
No, one quick question. Thanks for all the very useful information. One question. Given all this thing, Do you work with a lot of cloud vendors like AWS and Azure? Any of them give you support for a mock drill? For example, I want to be production ready, but it'd be nice to have the good feeling that a cloud zone did, or at least simulated failures. That way, I can do a drill of that kind of thing, or partial failures, etc. And you mentioned things like network failing, things like something's failing. Is there a way to these cloud providers offer this some kind of a mock drill that you can test your make sure feel confident that your product is behaving as expected?
I haven't. It's a great question. I haven't.
Okay.
I think if I wanted to do such a thing, if I were in Kubernetes, right, I'd have a lot of tools that I could go to my SREs and say, oh, hey guys, write a script that deletes this network hook, right? Okay, so if an SRE is going to understand the way everything's working, right?
Yeah,
And
I'm
probably
using a lot
have
of
some
AWS services. I wanted to make sure that I would like say I'm using their firewall, their WAF, their entry ingress controllers, or Route 53, or any of those things. And I'm just saying that I want to make sure my system is good enough against those kind of failures as well. And maybe I have to make a determination when to do the hot cold switchover versus right. So the determination. I'm really looking for. Do they offer any mock drills? I know you have worked with a lot of the cloud providers. I'm just curious.
So this is kind of related. I'm just going to share this link here. It's what they call the fault injection simulator on AWS.
That's what. Okay.
So that might be something of interest to you. So again, because everything's going to be architected a little bit differently. So there's no one general toolkit to do this for everybody.
Thought about something on the lines. That's good to know.
Yeah. But definitely there's a lot of stuff. If you Google like your cloud vendor and chaos monkeying, or your cloud vendor and fault injection, or that you'll probably come up with different test rigs for different services. But yeah, you may have to come up with your own. And that's why I was suggesting, for instance, torpedo testing. What happens when a node goes down, right? How many QPS can you maintain? What happens to your P99s, right? So you should definitely be, and that should be long before you get into production. You should understand how a degradation of your cluster could impact performance, right?
Exactly. Okay, got it. Yeah. And the only things there are things we control, and there are certain things we don't control, and that's what I worry. Like things like.
Right. I mean, everybody knows that if DNS goes, everything else goes to hell, right? So
it's always a trade-off, right? We go for a more complex DNX, then I have to pay more, and so it's always a trade-off as well.
Exactly.
Yep.
Thank you for the useful info.
Thank you, everyone, and hope to see you in the next meetup. And the recording, I will share the link to the recording on our StarTree Slack on the event channel. So stay tuned and make sure you join the channel. Thank you so much. Thank you, David.
Thank you, everybody.
Bye, everyone. Have a nice day.